Hello, my name is Sean Zong, and this is my Physics 2211 Lab 3 report on black hole. So before I begin the presentation, I'll just go over the contents of this presentation. First, we'll go through the introduction, which discusses the purpose and fundamentals of this lab. Second, the procedure, where I'll discuss the experimental setup and results. Third, the coding section, where I'll show my computational models. And fourth, the section where I'll answer the what if and what does it mean questions. So the purpose of this experiment is to determine the mass of a black hole based on a star's orbit, and then this information will then be used to determine the necessary initial velocity of a rocket ship that flies around the black hole without crashing into the black hole or the planet it was launched from. So here are the two fundamental principles that we really need to do this experiment. First off, Newton's second law, which can be expressed as the change in momentum over change in time, or the net perpendicular force plus the net parallel force. Here are the equations shown for both of those things. And then also the universal gravitational force, which is equal to the gravitational constant g multiplied by mass 1 by mass 2 divided by the distance r squared multiplied by r hat. And then here's also the magnitude vector, which is essentially the same with r hat. So for this experiment, there's some important assumptions that we're going to have to make. So firstly, the only force acting on the star is going to be the gravitational pull from the black hole. Therefore, the net force is equal to F gravity. Secondly, the calculation of a universal gravity is non-constant. So instead of using an average velocity value, are going to be replaced with a final velocity value. Third, changing the F net perpendicular will change the direction of the object. And then to go into like the experiment a little bit, first we're going to calculate the mass of the black hole in part 1 using known data implying Newton's second law. And then secondly, we're going to use the black hole mass and plug and check initial velocity conditions for this spaceship. So here's the code for the first computational model. As you can see in the top left here, I've just replaced data with like numbers that we already know. Delta t here is just equal to the number of seconds in a day. So this middle section of code right here is just filled with a bunch of momentum definitions, and just all this stuff is just writing the definition of momentum over and over again in different ways to get the values that we want. And then here the mass of the black hole is equal to, we use the universal gravitational formula here and just set the mass of the black hole equal to itself by itself on one side, equal to all these values derived from the equation, and that's what we have right there. And then here, this arrow stuff right here, it's just to show the perpendicular and parallel forces, forces that are acting on the object at that time. So the results right here, the mass of the black hole we got was 2.34 times 10 to the 34 kilograms. And here are the values of the magnitude of F net parallel, and F net perpendicular, as you can see in this picture right here. And also, I will say throughout the entire run, F net parallel was much lower in magnitude than F net perpendicular all throughout, which makes sense. Here, the code for the second computational model, I've just replaced the black hole mass with what we recovered from there. This ship speed value right here, this is the initial velocity, which I had to plug and check throughout running the code over again to see if what values would best suit the spaceship's goal, which is just to pass through over the black hole. And these values ended up working. Here on this middle huge block of code right here, we just have a bunch of we have like the universal gravity constant redefined over and over again so that we can get the values that we want for net force on with each object acting on each other, and then we can finally calculate net force overall. And then here in this bottom right here, we've used the position replacement and velocity replacement formulas to be able to find the planet velocity and position and the ship velocity and positions. So here is the graph that we received from that, where the purple line represents the spaceship's movement. So the initial velocity of the spaceship that we calculated here is negative 7 times 10 to the negative 6, y component 1.25 times 10 to the 7th meters per second, and the closest distance between the black hole and the spaceship ever is 6.48 10 to the 9th meters. So some possible sources of errors that could have occurred were that the first off, the mass calculated, the program could have run a bit longer period to calculate a more accurate average mass, and then the initial velocity was determined using guess and check, so there's obviously more optimal initial velocities for which the spaceship gets closer to the black hole. So for the first question, although the magnitudes of net force and its parallel and perpendicular components are the same as the rate of change in momentum and its parallel and perpendicular components, the two can be calculated in different ways. Since the net force uses mass times acceleration, which takes account of all of the forces acting on an object, change in momentum is just final momentum minus initial momentum and can be solved for using mass times velocity. So change in momentum is generally easier to solve for when multiple forces are acting on the system. And then for the second question, where we want an orbit, I just re-plugged guess and check numbers, and I got an initial velocity of negative 2.9 10 to the 6 for the x component and 1.25 times 10 to the 7th for the y component, and it made an orbital thing. But yeah, that's about it.